So we're going to speak about the different types of muscle fibers, and we're going to speak about the basis for these differences with muscle fiber types. Now, the first thing we want to understand is that a muscle fiber rather, has two names. The first name of that muscle is going to be the velocity of its contraction. So we're going to describe a muscle fiber type. The first name is going to be based on how fast does that muscle contract. So we have fast fibers, versus slower or slow fibers. The last name or the second name of that muscle is going to be based on its primary source of ATP. Where does it generate its main source of energy? And it can be oxidative, it can be an oxidative fiber. And what do you think the main source of oxidative fibers generating ATP? Oxidative phosphorylation, which requires oxygen, okay? Or it can be a glycolytic fiber. And what do you think the main source there is? Glucose. What process though? Glycolysis, right? Anaerobic glycolysis. So we don't need oxygen here. So these are the bases of how we distinguish different muscle fiber types based upon the speed of their contraction, that's the first name, and then based upon its primary energy source, that's sort of the second name. Okay, so let's speak about how we get these two different speed types. So depending on the rate of myosin ATPase activity in that myosin head, we can have a fast fiber versus a slow fiber. So if ATP hydrolysis happens really quickly, this is sort of the rate limiting step of determining how fast that myosin head is going to be. So it can have a fast rate of ATPase activity, that's going to make it a fast fiber, or it can have a slow rate of ATPase activity, that's going to make it a slow fiber. And all that really means is that, let's say we have a slow fiber that can contract 10 times in a second. We have a fast fiber that can contract 100 times in that same second, okay? So its rate of myosin ATPase is just faster, and that makes it a fast fiber versus a slow fiber. And we'll talk about areas of the body where we can see these different types of fibers. Now, the second factor that makes a fiber fast versus slow is its rate of relaxation. Now, what did we say is the main part of muscle relaxation? What has to happen? What has to happen for muscle relaxation? The lack of calcium. Calcium has to leave the cytosol. And so if we have a faster rate of this calcium ATPase activity, this is that calcium pump that's pumping calcium back into the SR. And the faster that can happen, the faster the muscle can relax. And so a fast fiber has a fast rate of its myosin ATPase activity, but it also has a fast rate of its calcium ATPase activity. So it's going to contract faster, it's also going to relax much faster, okay? Whereas a slow fiber, just like we said before, is going to take a longer time to relax simply because it has a slower rate of calcium ATPase activity. That calcium is being pumped out of the cytosol at a much slower rate, okay? And again, using this example, if a slow fiber can contract 10 times in a second, right? A fast fiber is going to contract 100 times in that second. It's going to relax 100 times in that second, right? It's going to contract and relax much faster than a slow fiber. Okay, so here are some examples of fast versus slow fibers, and we have an sort of a range here. So the extraocular muscles are an example of a fast fiber, and as we can see, they not only contract faster, right? This upstroke is the contraction, but they relax much faster as well. And so they're going to get to their maximum tension much more quickly than, say, the soleus muscle, right? The gastrocnemius muscle is sort of in between here. This is a powerhouse muscle. So it's not as slow as the soleus muscle. The soleus muscle is more for posture and maintaining our posture mainly, whereas the gastrocnemius is important for walking, for our gait, for kicking, running. And so it's going to be a little bit faster in its rate of contraction and its rate of relaxation. Whereas we can see the soleus muscle has this slow, steady, longer, more sustained contraction, okay? And all that this means is that the extraocular muscles have a faster myosin ATPase activity, a faster calcium ATPase activity. The soleus muscle has a slower calcium ATPase activity. and a slower myosin ATPase activity. Okay, all right. So that was the first name of the fiber, whether it's fast or slow. The second name of the fiber is based upon its main source of ATP, its primary source of ATP, right? Keyword primary, okay? So it can be mixed with other fiber types, but where is it getting most of its ATP from? So on this basis, we have glycolytic fibers and oxidative fibers. So glycolytic fibers mainly use anaerobic glycolysis, okay? And so they do not need oxygen here, right? We don't need oxygen to conduct anaerobic glycolysis. And so we have fewer mitochondria. Why do you think we have fewer mitochondria? Why would we have fewer mitochondria in a glycolytic fiber? What happens in the mitochondria? Or what process takes place in the mitochondria? ATP is made via what mechanism? Oxidative phosphorylation, right? We're not using oxidative phosphorylation as our main source of energy here. So we don't have a lot of mitochondria, right? And that makes sense. What we do have a lot of are these glycolytic enzymes and lots of glycogen stores, because our main source of ATP is breaking down that glucose, breaking down that glycogen anaerobically to make our ATP. So we use little oxygen. This is anaerobic. And these fibers have a larger diameter. And the reason they have a larger diameter is because we don't rely on the diffusion of oxygen here. Again, because we're not reliant on oxygen, because this is not heavily involving oxidative phosphorylation, we don't need a smaller diameter. We don't need to have oxygen diffuse into this muscle. And so we can get away with having a larger diameter in these fibers. Also, these are quick to fatigue. What about anaerobic glycolysis would make you think these are quick to fatigue? What's that price to pay of anaerobic glycolysis?
Can only go for a short period of time.
It does, yep, it does. But there's something that happens that we talked about a little bit last week or on Monday. What happens in anaerobic glycolysis? What happens in high intensity exercise? Lactate, good. So that buildup of lactate, that buildup of lactic acid is what really contributes to this quick fatigue in these types of fibers. All right, so these types of fibers have a larger diameter. They're not reliant on oxygen, okay? They have few mitochondria, but they have lots of glycogen stores, lots of glycolytic enzymes. And because they're generating ATP quickly, they fatigue. They fatigue because of that buildup of lactic acid as pyruvate gets shuttled off into that pathway. And so we get that price to pay for that quick supply of ATP. Let's look at, oxidative fibers. Now, oxidative fibers are just the opposite. They're mainly reliant on oxidative phosphorylation. And so as you would guess, they have lots of mitochondria. Okay, this is the site of oxidative phosphorylation. And so these fibers have lots of mitochondria. They have lots of myoglobin. Myoglobin is the cousin of hemoglobin, which is that transporter. It brings oxygen from the blood into muscle tissues. And that makes sense, right? We need oxygen, so we need lots of myoglobin. Now, the myoglobin makes this tissue appear more red. And as we can see in this staining, we have different types of fibers, but the oxidative fibers are darker staining, okay? Whereas the glycolytic fibers are more pale or whiter staining. And so this is where we get that white meat versus dark meat when we talk about different meat or different types of protein sources, right? So the dark fibers are dark because of the presence of this excess myoglobin, right? That red meat or that dark meat. Whereas the white fibers don't have all of this myoglobin, and so they appear more paler or lighter staining. We can also see that these fibers have a smaller diameter, and they're surrounded by many capillaries, right? These dark staining spots around the muscle is representing capillaries. Why do we need lots of capillaries in these oxidative fibers? Why do we need lots of capillaries here? What are our capillaries bringing in? Oxygen, right? Oxygen. So having lots of capillaries, having a smaller diameter so that that oxygen can diffuse across the capillaries and into the muscle is really important with these oxidative fibers, okay? Now, as you would guess, they're much more resistant to fatigue. One, because oxidative phosphorylation is a much more efficient source of ATP production, right? It's going to generate much more ATP. Two, because we don't have the buildup of lactic acid here, okay? So these are the types of fibers that we see in slow conducting muscle. And as you think about oxidative fibers, think about a long distance runner, right? His muscles are conditioned this way. He has lots of this type of fiber. He's going to be able to go for long distances, generate lots of ATP much more efficiently. He can maintain a somewhat comfortable rate of breathing, whereas a heavy lifter or a sprinter will have more of this type of fiber, right? This is why he's going to fatigue much quicker. He's not going to be able to sustain that heavy load for as long as a long distance runner would be able to run, okay? So these